Hello. Hopefully we're live here. Yeah, it looks like it's working. Is it working? Yeah, looks like we're live. Okay. So I'm studying the Fibonacci sequence. I'm sure many of you know what it is. I don't really care to explain it. You have the first few terms here. And let's say we start with these two terms. If you get the next term by adding the previous two terms. So 0 plus 1 is 1, 1 plus 1 is 2, so on. That's the Fibonacci sequence. Most people interested in math know this, so I'm not going to belabor that. There's this paper here. So I'm interested in Pisano periods. There's this paper here, so let's go up to the top. It's in the archive or whatever. You can find it. Archive has, and here's the URL, you can find it that way too. The archive has this nice new, I guess, beta format thing here. Anyway, so this is a recent paper. It's from, I believe it was submitted last year. Or, I don't know if you really submit papers to the archive so much as you just upload them, but I'm not sure exactly how it works. Okay. I'm occasionally going to check back here because the microphone, sometimes the microphone likes to quit on me. It's really annoying. And I can't have two displays yet. I don't think I have the right drivers installed for my graphics card here. Anyway, whatever. Yeah, actually, this is going to really bother me. So actually, I'm going to do something silly. I'm going to keep this on the screen so I can check the mic that it's working correctly. Okay. Anyway, let's dive into this. Well, anyway, this paper. I was asking Gemini a question. So there was a statement. So we're talking about the rank. All right. So let's just go through the beginning here. So we're interested in the period. Pisano period. So to give you an example of this, let's say, for example, in base 10, how we normally do things. You could look at the first digit. So you can keep doing the Fibonacci sequence. You keep going along and along. And a question might be, does this converge to some number? For example, if you've ever heard of p-adic numbers, there's certain things you can do where the number converges. You can have these p-adic integers. So that was the first thing that got me interested in Pisano periods. I was thinking, like, as the Fibonacci sequence goes to infinity, does it converge to some kind of number, or how does that work? And yeah, it might be really hard to believe, but I'm actually interested in this stuff because I think it connects to physics. But I think, you know, most people aren't going to believe that. That's fine. Really, really roughly, the symmetries of the dodecahedron and the icosahedron, and also they have there's a four-dimensional sort of versions of those called the 120 cell and the 600 cell. These, I don't know if I want to explain it. There's something called the geometric Mackay correspondence, and there's ADE graphs and all this stuff, and there's the E symmetry, and if you look online you can find all this E8 unification of physics blah blah blah, and so somehow these type E symmetries are seemingly connected with the symmetries of the icosahedron, dodecahedron, 120 cell, 600 cell, and so on. So that got me interested in really studying the dodecahedron. My motivation, I want to understand the four-dimensional analogs. So the 120 cell and the 600 cell. And as a warm-up, I wanted to, well, before studying these four-dimensional analogs, I thought I should really master the dodecahedron and the icosahedron and all the symmetries that go on there. And yeah, so in previous live streams, maybe several months ago, maybe even 6 months ago or something, I did a bunch of stuff in Blender studying the dodecahedron particularly. And I was interested in, you can embed a cube in a dodecahedron 5 different ways. And I thought that was interesting because this is all telling us something about 3 dimensions. These are symmetries in 3 dimensions, right? So if you give me a coordinate axes in 3 dimensions, so you have your x, y, and z axes, there's, in my view, let's think, there's at least 2 sort of canonical ways that I can build a dodecahedron from the axes that you gave me. I won't go into too much detail there. If I had Blender in front of me, I would maybe like show you that, but anyway, you give me a coordinate axes in 3 dimensions. The reason I'm phrasing it like that is because when you have 3-dimensional space, there's a bunch of ways to choose axes, right? And so in the language of linear algebra, I suppose that would be, what would that be? That would be choosing a set of basis vectors in R3, right? So there's ways you can do that. Okay, great. Now, there's the obvious way to do that is that you have the unit vector in the x direction, the unit vector in the y direction, the unit vector in the z direction. But then given that, you can look at like what are all the possible other basis sets of 3 basis vectors that we can choose. And that's basically the same question as how many, you're basically asking how many ways can we rotate a sphere, right? Anyway, I don't want to get too much into that. But I was studying the dodecahedron and how you can embed cubes into the dodecahedron. And there's some interesting things there. One of the things I found is, and when I say found, I don't mean that this is unique. I'm not like discovering this for the first time for humanity or something. I'm just saying I found it for me personally. You can look at a dodecahedron and you look at, so I was interested in how these cubes are embedded in the dodecahedron and how I could think about transforming from one cube to another. Now these are all of this is centered on the origin, or at least, we might as well think of it that way because it's easier. So the dodecahedron is centered around the origin, and these 5 cubes are centered, or they have the origin as its center. And so question is, how many different ways can you rotate one of these cubes to another one? And how to think about that. That was actually kind of the main motivation, among other things, but that was probably the main motivation for studying the dodecahedron in Blender, which I did on a bunch of live streams. But and so the answer is, well, you can create rotations using certain axes. Those axes will go straight through any of the faces of the dodecahedron. And so if you want to do that, you can just do that like that, or you can think of the dual of the dodecahedron, which will be the icosahedron, and the vertices of the icosahedron will correspond to the faces of the dodecahedron. And so you can talk about the axes that go through the vertices of the icosahedron, and they also intersect with the center, the origin. And so there's 12 vertices in an icosahedron, and so you end up with 6 lines. So 6 lines, they go through all of these lines go through the center, the origin, and they go through 2 vertices of the icosahedron. So 12 vertices of the icosahedron, and these form 6 lines. And those 6 lines then can be used as axes of rotation on the cubes that I was talking about before. And you rotate by 1/5 of a full rotation. So what is that? Is it 5 pi over 2? I don't know, tau over 5, whatever. So anyway, no, I think I got it backwards. 2 pi over 5, yeah, that makes sense. 2 pi over 5 is the rotation. So it's just 1/5 of a full turn, because after you do it 5 times, you get back to the original, and it forms 5 cubes. But what's interesting is that you can take any of these axes of rotation and do it. And I haven't really done it, but I want to convert all of that into quaternions and look at, because when you're using quaternions, you're multiplying by a quaternion, and you're not necessarily thinking about an axis. Anyway, so yeah, I haven't really gotten or transferred that into the language of quaternions. But you know, the vertices, when you look at how to construct dodecahedra and icosahedra, you inevitably the golden ratio comes up. So the golden ratio just comes up. So we can ask it, how do I construct an icosahedron? Now the golden ratio comes up just when you have a pentagon. Oh, it's having trouble, huh? Come on, Gemini. Gambatte kudasai. What's going on here? How do you construct an icosahedron? So in these live streams I mentioned that happened quite a bit ago, I was doing this in Blender programmatically. So anyway, so I mean, for a dodecahedron, you can start with a cube. So these points like 1, 1, 1, 1, negative 1, 1. Basically, so we're in R3, and we have 3 1s for the components, and then you have, well, it's plus or minus 1, plus or minus 1, plus or minus 1, right? That gives you 8 vertices of a cube. So you can start with that. But anyway, let's see. I asked for an icosahedron. Oh my god, it's talking about paper and stuff. That's not what I want. This is what I wanted. So you can see there's the these are cyclic permutations of 0 plus or minus 1 plus or minus phi. Now you might think to yourself, well, can we get rid of this phi? For example, I'll divide everything by phi, because that would just correspond to a scaling. Well, if you divide by phi, you'll get plus or minus 1 here, and then you get plus or minus 1 over phi here. So you've just turned it into 1 over phi instead of phi. Alternatively, you can multiply everything times phi, and you'll get phi plus or minus phi here, and then you'll get plus or minus phi squared, which ends up being plus or minus phi plus 1. So it's one of the nice algebraic properties of phi, is that when you square it, you get phi plus 1. So again, this is the golden ratio, which is defined as 1 plus root 5 over 2. You can also define it from, let's see here, x squared minus x plus 1 equals 0. I hope I got that right. Maybe I didn't. You can look it up. This will actually give you 2 solutions. So it'll also give you negative 1 over phi as a solution, which sometimes people write as a psi. I'll just call it psi because this is very hard to pronounce. Give me the Greek letter psi, capital and lowercase. So anyway, yeah, so if you're going to build a icosahedron or a dodecahedron. I hate how it... Did you see how it grabbed it and brought it down? Oh man, that makes me want to... If Google were a person, I want to punch them in the face every time that happens. Anyway, psi, yeah. Usually we're going to have the lowercase psi. I'm going to say psi because it's easier. Anyway, so that corresponds... We use this symbol for -1/phi, which is also going to be 1 minus √5/2. So those are the solutions of that equation. If I got it right. Anyway, you can look it up. Okay, so the point is we get phi everywhere, and anyway, let's see. I mean, for like 9 months, I wasn't doing that much math. From last year June to maybe whenever I stopped doing many live streams, like a couple months ago, like the last couple months, I've done very few live streams. So the last couple months I've been focused on math. That's why I'm not doing... I also wanted a break, but from live streams a bit. But anyway, let's get back to this. So blah blah blah. So I've just been sort of continuing my studies of the golden ratio and various things. And whereas in the past I was focused on the dodecahedron and the icosahedron and like just really doing deep dives and really trying to understand all the symmetries, and there's a lot more work for me to do there. I mean, the icosahedral group, I think it's called, I think it's a group of order 60. I think it's A5. Tell me about the icosahedral group. So this will tell you the symmetries of the dodecahedron or the icosahedron. They have the same symmetries because they do. They're duals. So a nice way to think of that is to think of... Let me think. So you have, in 3 dimensions, you have edges, vertices, and faces, right? And, oh god, I hate the glazing. I hate the AI glazing. Okay, they're saying it's a fascinating concept. Lately, AI, they're always saying like, "Oh, that's such a great question. You're really getting at the heart of the matter." And I'm just like, I hate being praised by a machine. It really bothers me. But I guess some people out there are uplifted by that. But for me, it's the opposite. I hate it. Anyway, I guess they're not glazing me here. But all right. So the icosahedral group. So okay. So in 3 dimensions, you got the faces, vertices, edges. You can have a vector for each of those. So for the edges, make a vector from the center, call it the origin, to the midpoint of the edge. For the vertices, it's obvious, right? You make a vector from the center to the vertex. Wow. For the faces, to the center of the face and so on. So when you have this collection of vertices, if you do that for the icosahedron and the dodecahedron, they're duals of each other, you end up with the same vertices. It's just that the vertices and the faces will be switched. That's all. So it gives you the same symmetries. Okay? Blah, blah, blah. I believe this has order 60. And it's isomorphic to A5, which is an alternating group of 5 elements. And I think that's, it's all even permutations of 5 objects. So if we're talking about all the permutations of 5 objects, that's called the symmetric group of order 5, denoted S5. So it'd be like this with an S instead. The symmetric groups, symmetric groups, SN, they're like the big daddies in group theory, because there's a theorem, every finite group is a subgroup of some symmetric group. So no matter what group you give me, and that includes like the monster and all these crazy sporadic groups. I think there's, how many sporadic groups are there? Is it 26? I don't know that much about sporadic groups. How many sporadic groups are there? I think it's 26. The monster is one of them. It's this enormous sporadic group. And sporadic, we just mean that it's not part of a pattern. Like there's a few families of finite groups. 26. There's the baby monster, and the largest of all of them is the monster. John Conway was real important in all this. So yeah, you have the classification of finite groups. It's a big thing. We're not going to talk too much about that. So the icosahedral group has order 60, or it says right here, and it's isomorphic to the alternating group A5. So anyway, I have more to study here. I'm not a master of these things by any means, but my study has sort of transmogrified. It's transformed from being just about the dodecahedron and the icosahedron to studying Fibonacci stuff for reasons that I will leave as an exercise to the viewer. Okay, so, and this is a recent paper. Yeah, I was studying this, and I thought, well, maybe I'll do a live stream. And how long have I been streaming? 21 minutes, and haven't even gotten into this. I've just been talking about context, whatever. So Pisano periods are when you do the Fibonacci sequence and mod some number. Okay. So, for example, if you did it mod 10, then what does that mean? It means that you're doing the Fibonacci sequence, and you're only concerned with the first digit. So, if you did it mod 2 instead, well, that would mean it's sort of like you're doing the Fibonacci sequence in binary, which is a good exercise. But you're doing the Fibonacci sequence in binary, and you're only concerned with the first digit. In other words, you're only concerned with whether it's even or odd. And so you just write a sequence of ones and zeros, where 0 corresponds to even and 1 corresponds to odd. So I think it's fun and interesting to do the Fibonacci sequence, mod some number, or just do it in some base. So, for example, if you're doing it in base 5, then you are interested in the Pisano period. You're basically working out the Pisano periods. Well, to figure out the Pisano period, you have to look at how long it goes before it repeats. Okay. So today, this content is better for people who are already familiar with the Pisano period. There's a good video or two on YouTube. And the thing is that there are a lot of, this is in the territory really of open problems. There are I'm not going to spell everything out totally, but to give a simple concrete example so that someone who didn't know what a Pisano period is, so that they can follow along. Here's a real good concrete example. If you're interested in the Pisano period, for the number 10, so we'll see it down here. So hold on, pi of m. So we denote the Pisano period like this, pi of m. So if you're interested in the Pisano period of length, let's see, as a length of 1. Yeah, so the Pisano period modulo 10, for example. That's basically saying the Fibonacci sequence, mod 10. In other words, you do the Fibonacci sequence, and you're interested only in the first digit. You don't care about the rest of it. So you can do this on paper and see how long does it take before the sequence repeats. It will eventually repeat. And so it actually says that here, 60. It will take 60. So that's kind of a long exercise for modulo 10. Shorter exercise might pick a smaller number, like mod 5, for instance. Okay, so yeah, I'm not going to spell this out anymore. If you're new to words like modulo, you're going to have trouble following along. Sorry about that. but it's just the way it is. I have to start somewhere, and the rest of this content is going to be better for people who already understand Pisano period. Yeah. So the Pisano period is denoted by, and now this has nothing to do with 3.14. This is just a Greek letter pi. They denote it like that, and yeah. So the closed form, general formula for the Pisano period is not known. Yeah, so I sort of think of it as sort of the general structure here of Pisano periods. I think maybe we understand it, but we don't have proof. So there's conjectures related here. Actually, I mean, I think it depends on. Let's see if they get into it here. There's this thing called the Wall-Sun conjecture. I don't know if they bring it up here. We're not even halfway through the paper. Wall-Sun primes. So there's this thing called a Wall-Sun prime. That's a funny name. So it's actually these twins, Sun and Sun. I think they're Chinese, and a guy named Wall. So it's just funny to call it the Wall-Sun prime. But probably it should be pronounced Wall-Sun, I guess. But yeah, so I don't have time to go into it, but there's an interesting thing about this, and so we don't really know it for sure whether these exist or not. As far as we have studied, like people can use computers and test, right? So we've tested an enormous number of numbers, and we haven't found any of these primes yet. However, there is, I guess, according to some people, there are reasonable reasons to believe that we just haven't tested enough that they may exist, and but they might be extremely sparse. Okay. Sorry, I can't go into more detail about that. Also, this is an interesting matrix right here. So if you put a 1 here, and then you just multiply, square it, cube it, and so on. Just do matrix multiplication, you'll find that you end up with the Fibonacci sequence occurring. And it'll be like this. So for example, you have, the Fibonacci sequence, it goes 0, 1, 1, 2, 3, 5, 8. So for example, you'll get an 8 here at one point with with 5s here and here. This is really annoying that this keeps coming up. So imagine a matrix with an 8 here, a 5 here, a 5 here, and a 3 here. That would be amazing. Well, that's what you get when you multiply this out. So that's cool. We can sort of convert all of this beautiful stuff into matrices. Nice. And I believe this K Fibonacci stuff is we're not necessarily only concerned with the Fibonacci sequence itself, right? We can think of ways to generalize this. And I guess no matter what starting numbers you choose, I think you get the ratio of the terms ends up converging to the golden ratio. Unless, I think you can, let's see, if you choose 0, -1 as your starting terms, it goes 0, -1, -1, 0, -1. I think it just keeps repeating 0, -1, 0, -1. Okay, but other than that sort of pathological example, I think it will converge either to phi or psi that we saw earlier, because you can use negative numbers, right? And then you'll have this alternating sequence. And so in general, these are referred to, I believe, as binary recursion sequences. Let's see here. believe it's mentioned in the beginning. Binary recurrence sequence, sorry. So binary because the inputs are two things, right? You can also generalize this by looking at what they call the Fibonacci sequence, where you sum the first three terms, or the previous three terms, and so on. So there's various ways to generalize this, and I'm pretty new to this stuff, actually, so I'm not going to say too much more about that, but I've been digging around, and for example, there's like an old post from Tao, is his name Terence Tao? Famous mathematician. I think he's a professor at UCLA. And so I'm sure he studied this stuff a bit because he made a blog post about some of this stuff. Anyway, let's try to dive into it a bit more. So we have that for modulo 10, the Pisano period is 60, so that means it repeats every 60 terms. And you know that it repeats when you get the sequence 0, 1. Yeah, I'm not going to explain that. You can play around with these things or watch a bunch of videos, and you'll start to realize that, yeah, basically, once you get back to 0, 1, that's going to, well, you can view it as the start of the repetition of the period. Because, well, you'll get to 0, 1 the first time. I mean, the sequence will hit 0 and then 1, yeah? And then, so, because it's basically starting the Fibonacci sequence again. There, you see? Kind of back to where we started, right? And so that's why we care about the zeros in these Pisano periods. Okay? And I've been playing around with these myself and sort of realized, well, I have some thoughts about the zeros, but I think my thoughts were specified here somewhere, actually. We'll get to it. This is the part. Well, so I'm not sure. So there's an interesting, I don't know, theorem. I've seen this numerous times, that the Pisano periods have exactly 1, 2, or 4 zeros. And I'm not sure exactly why. So that's a real motivation. Actually, I think that's why I found this, or how I found this this paper, is because I Googled, like, I forget what I Googled, who cares? But yeah, I want to know how we know this. And the fact that they're equally spaced in the cycle is, I think, the thing that I was sort of finding. I mean, there's a lot of symmetry here. I think that, so say you're talking about modulo m, okay? In some ways, the number 1 kind of plays a similar role to whatever m minus 1 is. So I guess the analogy is like in base 10, so the ordinary decimal numbers that we use, you notice when you do the multiplication table, you notice 9 has a special property. Like when you go 9, 18, 27, 36, when you're writing out the multiples of 9, you notice that one of the numbers goes up and the other number goes down, right, by 1, right? 18, so it's 1 and 8. 27, we've incremented the tens place by up 1, and we've decremented the ones place down 1, right? And they always add up to 9. And when you do different modulos of numbers and write out the multiplication tables, you'll see that the m minus 1 always has the same kind of pattern going on. So that's cool. And I don't know how to explain it exactly, but somehow there's something there's definitely a symmetry going on, and it's in some way the number 1 modulo m plays a similar role to the number m minus 1. There's a symmetry going on, and it's related to this equally spaced in the cycle thing. So cool. So let's move on. The number of zeros in a Pisano period is the order of m, denoted omega of m. The rank of m is the index of the Fibonacci number of the first 0 in a Pisano period. which the rank is denoted alpha of m. In other words, the rank denoted alpha m is the index of the first Fibonacci number divisible by m. So this is an interesting thing. I guess that every Fibonacci number, for every prime, there is a Fibonacci number divisible by that prime. So I wanna elaborate on that a bit. So we'll just ask Gemini here: is it true? And they're probably going to reference the prior conversation because I chatted with Gemini previously about this. But anyway, so is it true that for every prime there is a Fibonacci number that is a multiple of that prime? In other words, the prime divides that Fibonacci number. Okay, and we will see that this is true because of something that has to do with the zeros of the Pisano period. So anyway, so yes, as for every prime number p, there's a Fibonacci number that is a multiple p. If you look at the Fibonacci sequence and take the remainders when each number is divided by a prime p. So in other words, if you look at the Fibonacci sequence modulo p, the new sequence of remainders is periodic. And so if you accept that it's going to be periodic, and I just realized I should explain why we know that's true, so I'll do that in a second. But if you accept that this is going to be periodic, then eventually it's going to hit 0. And the fact that it's hitting 0 means that modulo p, it's 0, which means that our Fibonacci number at that point is divisible by the prime p. So how do we know that it will be periodic? Well, you can look at your sequence of numbers in pairs, okay? Because each Fibonacci number is the sum of the previous two numbers. So we look at them in pairs at a time, and there's a finite number of possibilities, because let's say we choose the prime as our prime, we choose the number 17, for example. Well, or should we choose easier? Let's just choose 7. Okay, 7. So that means that we're taking these a pair at a time. So okay, so we have, for example, in the beginning it's going to be 0, 1. Okay. Next it will be 1, 1. Next it will be 1, 2. Then it will be 2, 3. Let's just go until the mod starts taking effect. So 2, 3, so it'll be 3, 5. We're taking pairs of Fibonacci numbers at a time. And the next one is 8, which mod 7 is 1. So it's going to be 5, 1. So because we're doing mod 7, the possibilities for entries in these ordered pairs, the possibility for entries is 0 through 6. So we have finite possibilities. So for the first entry, we'll have p possibilities, in this case 7, 0 through 6, that's 7 possibilities. And for the second entry, we'll have, again, 7 possibilities. So total for these pairs, we will have p times p, so p squared, in this case 7 squared. So there's 49 possibilities for what could be in these pairs. So that puts an upper bound. And so that means that eventually this has to repeat. Because once this repeats, it's just going to keep going around in a cycle. Like eventually this will get back to 0, 1, and then it will cycle again. That's what's going to happen. So if you kept writing this out, what's the Pisano period of 7? I think it might be 16. But anyway, so 5, 1. So you can just add the digits, you get 6. So it's going to be 1, 6. Next, it's going to be 6, 0, because 1 plus 6 is 7, which mod 7 is 0. Then we get 0, 6. Then what do we get? Am I doing this right? Yeah, 6, 6, right? 0 plus 6 is 6. Okay. And then we get 12, which mod 7 is 5. So it's going to be 6, 5. Should I just do this out until it repeats? Now we get 11, which mod 7 is 4. We get 9, which is going to be 2. 6. 8, which is 1. And we're going to get 0. Right? Yeah. And this one, 1 plus 0 is 1. So we're back at the start. And it's going to repeat. Right? It's just going to repeat. So how many was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then it repeats. So the Pisano period of 7 is 16. Right? Okay. So, and we've established that there's an upper bound. So the upper bound for 7 would be 7 squared, which is 49, because there's only that number of possibilities for the entries in these pairs. So the Pisano period in this case worked out to be 16, but the upper bound was 49. So 16 is less than 49, no problem. Okay. All right, so let's go back to this. So is it true that for every prime there's a Fibonacci number that is a multiple of that prime? Yes, it's true. For every prime number p, there's a Fibonacci number that is a multiple of p. Let's recap why. If you look at the Fibonacci sequence and take the... So if you look at the Fibonacci sequence mod p, this new sequence of remainders is periodic. We just established that. It must be periodic because there is a finite upper bound on the possibilities of these pairs. So it must repeat. So it must be periodic. Which also means it must come back around to 0. And this, when it comes back around to 0, hold on. So here we have 4 zeros, right? Does the first one count, or do we start at 1? I'm not sure about that, so I'm kind of learning this stuff in real time here. But if we don't count it in the beginning, it would count at the end. So I'd say we counted at the beginning, I think. We had 0 here, but these are pairs now, so we're counting, this got counted twice. So this is actually just 1 0. So I guess actually there's not 4 zeros. There's 1, 2, 2 zeros, I think, because this is again the first 0. We're back at the beginning. So I think there's 2 zeros here. Okay. So we talked about rank and hold on, I'm moving the mic here so I can check my notes. The rank, denoted alpha m, is the index of the first fn divisible by m. It's very confusing language for me. Anyway, appearance of 0. So 0 will appear anyway. Because that's how we determine that it's periodic, is when it must come back to 0 at some point. We know that it must be periodic, so it must come back to 0. So there will be some point where it becomes 0, and the fact that it becomes 0 at some point means that that Fibonacci number will be a multiple of the prime. So I know that might have been confusing, but Nobody said it was gonna be easy. Nobody said it was easy. Okay. Nobody said it would be so hard. All right. Rank of apparition. I don't know what this apparition thing is yet. So I was reading this today, and I just thought to live stream it. So I'm not an expert in this paper or anything. All right. Let's get back to the paper. So again, the number of zeros in a Pisano period is the order of m. So terminology there. And we denote it omega m. The rank of m is the index of the Fibonacci number. The rank of m is the index of the Fibonacci number of the first zero. Okay. So we have order is going to be the number of zeros, and the rank is going to be where the first zero appears. The sort of the index. If your Fibonacci number is f sub n, then that sub n, where the first zero appears, that's your rank. But then they said this part, which is what we just went and talked to Gemini about. In other words, the rank denoted alpha m is the index of the first Fibonacci number divisible by m, because that's where the where that first zero appears. So that's what we just talked about. There are two conjectures in, I guess this is some database of, is this the database of integer sequences, maybe? Anyway, there's two conjectures they want to talk about regarding which m has order 1, 2, and 4. And again, this paper is just from, can I go back? No. It's from last year, actually, okay? So anyway, so we've got some conjectures, and I don't want to go too long. I know that this is, if I'm going to go through this whole paper, we're on the first page still. It's going to take maybe 16 hours to go through the whole paper. So, yeah, I don't know why I live streamed. I just thought this might be interesting to other people, and so we're getting kind of an introduction. Let's look at these conjectures a bit. I don't know how long I'm going to go today, but anyway. Conjecture 1.1. An integer m has 4 zeros. Oh, okay, so I've already looked at this a bit, but the easiest way to describe this is it's basically that the order has 4 possibilities. There's either 1, 0, 2 zeros, or 4 zeros. Now, I've known this from watching videos on YouTube. It's mentioned sometimes. So I believe this was already known. The conjectures are about when exactly these happen. And it seems to be that if it's, if we're talking if n is 2 mod 4. So I think, for example, let's see here. So for m equals 14. No, that doesn't. That's wrong. 14's not there. N is congruent to 2 mod 4. How is 4 congruent to 2 mod 4? I'm confused about something here. That doesn't work. What's going on? What's going on? Splitting integers according to number of zeros in one Pisano period. Yeah, okay, I'm failing to understand. But anyway, the order is divided into these 3 possibilities. It can be 1, 2, or 4. And yeah, that's what these 2 conjectures are about. If you're interested in this stuff, so I might wrap it up soon. I know it's not, it's almost 50 minutes, so whether that's long or short depends on your point of view. But if you're interested in this stuff, this right here is the Legendre symbol, and it's related to quadratic reciprocity. So you have to maybe learn those. If you don't know them, it comes up. So maybe we'll explain that real quick. So maybe I'll explain quadratic reciprocity and the Legendre symbol. And then that'll be it for today. And so I'm just giving you the tools. If you want to learn more about this stuff, here you go. I think this paper sounds interesting to me, so that's what I'm studying. Yeah, and people who study a lot of number theory, they already know these things, but we'll just explain these, and then, because it comes up. It doesn't come up right away. If you're interested in Pisano periods and you watch some videos online, probably it might not come up. But yeah, if you start looking at papers and stuff, it will come up. So anyway, so that's interesting. I didn't know that. That's from Gauss, okay. So we have quadratic residues and non-residues. So basically, okay, so let's look at the example, mod 5. So 2 squared is 4. And the question is, so for 2 squared equals 4, the question is there a square in mod 5 corresponding to this? So for 1 and 4, the answer is yes. There is a square corresponding to the number mod 5. But for 2, it's not true, because the question is, we want to ask, is there a number mod 5 such that we square it and we get 2 mod 5? So is there a number where we square it and we get 2 mod 5? And the answer is no. So you just check for all of them, 1, 2, 3, and 4. So 1 squared is 1 mod 5, 2 squared is 4 mod 5, 3 squared is 4 mod 5 because it's 9, 4 squared is 16, which is 1 mod 5. So if you said to me, hey, I want a number that when you square it, you get 3 mod 5, I would tell you that's impossible. You can't, there's no number where you square it and you get 3 mod 5. If you told me, hey, give me a number where when you square it, you get 4 mod 5, I'd tell you, well, that's easy, 2. And I'm sure you could find others, right? Well, 3. Okay, so anyway, yeah, so it's sort of a weird, wonky kind of thing, but I think it's a pretty fundamental thing in number theory that is of interest. One thing that's interesting, I guess, is that what happens here is that half of the numbers end up being quadratic residues, and half of them are going to be non-quadratic. Wait, that must be wrong. Hold on. No, it's right. So, and we're not counting 0. So 5 for 5 here, half of them are quadratic residues because 1 and 4, and half of them are non-quadratic residues. So that's already, so if you want motivation for learning about this, why is that true? And Michael Penn has a series on quadratic residue, and he also explains the Legendre symbol. I think Michael Penn is a bit hard. I hope I'm getting his name right. Big math YouTuber. And, if you're looking for like really beautiful intuitive explanations, you want 3 blue, 1 brown. But he has less content because he works really hard to make everything beautiful. And then Michael Penn is basically like a math professor. You'll get those kinds of lectures. So anyway, and then the Legendre symbol gives you 1 or -1 depending on the whether you have a quadratic residue or a quadratic non-residue, modulo p. So in the previous examples, we were using mod 5, so our P would be 5, and then the A's are these 1 and 4. So in this example, 1 over 5 is going to give us 1 because it is a quadratic residue. And then 4 over 5, these aren't fractions, it's just notation. So 4 over 5 is going to give us 1, and then 2 over 5 is going to give us -1, and 3 over 5 is going to give us -1. So it's just notation. Hello, Zeus Kias. You're an hour late. Yep, you're an hour late. Sorry. Well, you can watch it. It'll be up, so you can watch it again from the beginning. And yeah, so this is notation that I guess is used a lot, Legendre symbol. And so yeah, I'm actually wrapping it up. And man, they give us a lot of blah 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 here. But so hopefully I kind of gave a basic explanation of what this is about. And so if we go back to the paper, that came up in the paper here. Here's the Legendre symbol right here. So yeah, this is what I'm studying and learning right now. My voice is starting to give. I haven't been recording videos for a while, and we're getting close to an hour, and my voice is starting to give way here. And I just wanted to give an introduction. So I was looking at this paper today. This is a paper from last year, and just looking at this, inquiry regarding the periodicity of the sequence modulo a positive integer has continued, and in 2004 it was proven by Everest and Sparlinski that every binary recurrence sequence is periodic modulo a positive integer. So earlier in this live stream, I talked about, I proved in air quotes, but I gave you the logic for how we know that the Fibonacci sequence is going to be periodic modulo some number. And so this 2004 result is not just for the Fibonacci sequence, which I think we've known that for a long time, but for any binary recurrence sequence. So this again is sort of a generalization of, if you think the Fibonacci sequence is cool and you want to generalize it, for example, with different starting values, or maybe, for example, you could triple the previous number and add it to the term, the n-2 term. So for example, so this is the Fibonacci sequence. We just add the prior two terms. You could put a multiples here, like 2 times fn-1 plus 3 times fn-2. Well, that's going to be some, and I think they often call it linear recurrence sequences. The fact that it's binary means that we have 2 inputs. Okay, so it doesn't have to be just binary, but in this case they proved it for binary recurrence sequences. So I think we'll just ask Gemini here, and probably gonna wrap up the stream after this. I keep saying that, but yeah, my voice is really starting to give way. Yeah, I think there's something like linear recurrence sequence or something, because linear, because the reason the word linear is used, if you look at this is a linear combination. If you don't know what a linear combination is, I'm sorry. But it's this. It's some amount of one thing plus some amount of another thing. And you could have more terms. But if you don't know what that is, linear combination, you can look it up and explore linear algebra. But let's see. So yeah, the binary part refers to its dependence on two previous terms. Most common and well-studied type is a linear binary recurrence sequence with constant coefficients. So that's going to be something of this form. It's a linear combination of the two prior terms. Some kind of linear combination. So for the Fibonacci sequence, we have 1, p equals 1, and q equals 1. And the starting terms are 0, 0, and 1. I mean, I sometimes I think I see 1 and 1 as the first starting terms, but 0 and 1 is fine. Anyway, yeah. So this allows us to generalize this. Yeah, again, if you think it's cool, and also, so something I didn't really explain too much, but the Fibonacci sequence, as you go to infinity, the ratio of the two terms. So, and people familiar are they already know this, but so if we talk about f of n plus 1 divided by f of n, okay? So we're interested in the ratio of terms. Then this approaches the golden ratio as n goes to infinity. So this is a way to get at the golden ratio. And I believe it was Kepler who found this. So like if you're poking around online, you'll see all this stuff, you know, Fibonacci golden ratio, they're connected, blah, blah, blah. There's all this, there's also a lot of nonsense out there, right? This is well known. People look at spirals like the spiral arm galaxies. People will take any old spiral and call it the golden spiral, basically. And so there's a lot of nonsense online, which is unfortunate because you don't need to embellish and exaggerate. You know, math is already beautiful, so let's just stick to the truth. But yeah, so basically you go through an evolution where the first time you find out about the Fibonacci sequence and the golden ratio, it's like, wow. And then you see a lot of stuff online that you find out is a bunch of BS. And then you realize, oh, or you think, well, it's all overrated. There's so much overrated BS out there. But then you get used to that, and that's old news. And then at some point you get interested in it again. Yeah. Anyway, so as it goes to infinity, it approaches phi. But the interesting thing is basically this is going to happen almost no matter what starting values you choose. Real. What is real? I'm responding to the comments. So the chat. So yeah, most of the starting values that you choose will approach phi. I talked about it earlier. If you choose starting values 0, -1, I believe that just flip-flops between 0 and -1. But if you choose two positive, let's say if you choose two non-negative numbers, so 0 or positive numbers as your starting values, I think it approaches phi. If you choose, like let's say you choose two negative numbers that aren't equal to each other, then the sequence will flip-flop between positive and negative, I think, but that ends up approaching a -1 over phi, I think. So anyway, so I shouldn't talk too much about stuff that I'm not totally sure about. But anyway, so if you pick two random positive numbers, you'll still have it approaching phi. I'm pretty sure of that. So it's not just the Fibonacci sequence that's special. And there's also the Lucas numbers. We didn't talk about that. And there's really interesting relationships between Fibonacci numbers and Lucas numbers. We're out of time to talk about that. Going from fascination to thinking it's BS to finding it fascinating. Yeah, exactly. That is the the Pokemon evolution here. Yeah. I don't know about Pell numbers, so I need to learn that. And I think we're getting to the end of the stream here. I think I've said a bunch of stuff. My brain is getting tired and turning into potato salad mush. So, all of this was part of the live stream until here. I just scrolled through all this stuff. Wait. No, not here either. This is where I started with the live stream. How do you construct an icosahedron? So, let's just look. I'll just scroll over this like what I was asking it. This is just related to the paper. So I was trying to understand the paper better. And oh, yeah, I don't know. I think it's weird AI stuff. I actually talked about this in a live stream. Anyway, that's it. Thank you. Have a great day. Bye-bye.